So good morning, and again, sorry for the delay. We started discussion about support vector machines in the previous class, and we'll continue that discussion in this class as well. So, what was the basic idea of support vector machines? Right, you maximize this margin. Suppose, let's say, I have some samples on this side and some samples here. On the other hand, now there are infinite possibilities of this classifiers. Now come up with that classifier which has a maximal margin. That is the very basic idea of it. And towards that, we made this, for example, this is anyway g of xi bar is equal to 0. Assume that you have here, let's say your yi is -1 for here, and this yi is +1 here. Assume that this is your omega1 samples and omega2 samples. So gi of xi bar or g of xi bar is made to what value here? +1. Correct. Good. And what about this? Very good. And in that scenario, what was the distance here once we made that to this line? Very good. Very good. So this distance is equivalent to 1 over norm of W bar. So the problem essentially boils down to maximizing 1 over norm of W bar, correct? And we made this into an equivalent problem of minimizing. What does that equivalent one we have taken? Right, minimizing, you find out, you play with W bar and such that is norm of W bar square, right? Subjected to the constraint. So if you just go on increasing W bar, it can go anywhere, right? It will go to infinity. What was the other constraint that we should have here? There should be no samples in between. And for those samples which are there here, for that, of course, this would be 1, right? For all the rest, it should be greater than 1 once you multiply it yi. So subjected to the constraint that, how do you compute g of x bar there? W bar transpose into xi bar plus W naught -1 should be, right, very good, greater than or equal to 0. For those points which are there on these lines, y, very good, yeah, that's a mistake. This should be multiplied with yi, because otherwise negative issue is there. So we consciously took -1 and +1 for that purpose. So subjected to the constraint that yi into W bar transpose times xi bar plus W naught -1 is greater than or equal to 0. This is all the gist of what we have discussed in the previous class. This is called as a constraint optimization problem because you are posing a constraint here. It is also a quadratic optimization problem because you have essentially a quadratic term here, the norm of this thing. So it is, to put it all together, you end up with a quadratic optimization problem that has nonlinear inequality constraint. I'm calling it as, I'm being very specific here. This is an inequality. It's not like equal to 0. It is greater than or equal to 0, less than or equal to 0. That's an inequality. So it is a nonlinear inequality constraint. This is one way to look at this problem. Now, after this, the rest becomes, how do you solve a optimization problem? That is what it boils down to. This is one way you look at it. And the moment you have some constraints to be included, what is the very commonly used one for a quadratic optimization problem with nonlinear constraints? At least the name, we have talked about the name in the previous class. It is Lagrange multipliers. using Lagrange multipliers, you will solve it. Again, this is also, you will come across this optimization in various places, not just this course, in different places, but even in other courses also later on. And this is something you should always have a hold on. So we will give some intuition, but nevertheless, that won't be sufficient if you want to get a good mastery over it. So please do read about it. Any standard textbook has it. Wikipedia has it. You all the tools will allow you, including your MATLAB, Python, whichever you want to use. They allow you to solve problems like this, where you say what is the problem to be solved, what is the constraint to be posed, and then choose various other required things. So this should be a kind of a very comfortable thing for you to do in the long term. So, but anyway, this not being a optimization course, we will not be able to do a thorough job here. Nevertheless, I hope that you will get some good intuition at the end of this class, as well as maybe the next class also. We will see it in little more detail. Okay. So how is this done here? Is you convert, let's first write it as a new function to be optimized, L of, I have already the variables W bar and W naught are already there here. So W bar is there, W naught is there. And I would include another thing, set of variables to be optimized, referred to as lambda bar, which is giving you a weight to this constraint added to your original problem. Okay, so now your problem is you minimize this, okay, function, which is now we are defining it as half of norm of W bar square, okay, plus, should I keep plus? This is a minimization problem. I want to write it as, well, this is greater than or equal to 0. So I would put minus there so that this maximization is equivalent to a minimization there. So I'll put that. And then, well, I have I varying from 1 to n. I have assumed that I have n samples in my training data. So what can I do here? I is varying from 1 to n. And let me give a weight to each of them, lambda I. That's what this all a vector of lambda 1 to n. That is what I am referring to as lambda bar, the new parameter introduced here, lambda I times yi into W bar transpose xi bar plus W naught. Okay. Well, this lambda I is for the whole constraint. So I would apply it over the whole, this minus 1. This is my new minimization problem. Is that clear what I have written? All I did simply is, this is equivalent to, if I add a negative sign here, less than or equal to 0. I have to minimize that. That I brought here. See this, these, how many constraints are there? If you have n training samples, for each xi and yi, you have one inequality here, correct? Now, for n inequalities, each one I am giving a weight of lambda I for each, lambda 1, lambda 2, lambda 3, so on to lambda n. I am calling that with a vector lambda bar here. This is a very, very common step again, irrespective of the other problems that you may encounter where you are applying Lagrange multipliers, you would use a very, very similar strategy. So these steps have to be clear. The inequality for me, this is my minimization, original minimization problem. My inequality, I converted into an equivalent minimization problem. So this greater than or equal to 0, I made it to less than or equal to 0. And of course, you should have already noticed here that this lambda I should be, of course, greater than or equal to 0. Otherwise, this minimization would become maximization, is it not? So I will choose my, should choose my parameter lambda I such that it is positive, right? What else next? So this is one problem you could solve. Here is again another algorithm called primal dual algorithm. So one way is, of course, this constraint problem you solve by solving this equation. That is one way. There is another way to solve. You see in its parallel world, what is an equivalent problem, which you refer to as a dual problem. If you minimize your dual algorithm, that will obviously, if you optimize, I consciously purposefully use optimize rather than minimize. If you optimize that problem, dual problem, that will automatically will give you a solution here, which optimizes this particular, your primal problem. Okay, this again, primal dual algorithm, Lagrange multipliers, they come in package. Okay, so you typically, there will be many instances. You will see why solving this dual problem is a worth doing rather than the primal. You will realize it shortly, but right now take it for granted. Then again, I'm not going to the details, but there is something called as KKT conditions. Nothing to do with Kolkata Knight Riders and all. This is KKT. There are 3 other scientists' names. Okay, I'm afraid of my pronunciation about those scientist names, so altogether I'm skipping that. You see those names. These are called as KKT conditions, which will tell you how to obtain its equivalent dual problem. Intuitively, we will not go into any rigorous math here. Intuitively, all it does is very simple. How we were minimizing an equation functional earlier? You take derivatives. You exactly do the same thing here. As simple as that. So what are the derivatives that you would take here? For example, I could take do L of W bar, W naught, lambda bar with do W bar. Just which are my parameters? W bar, W naught, lambda bar. You take derivative with respect to W bar, of course, which means it should be there in your mind that it is not a single derivative. It is, if your feature vector is of L dimension, this is it is a vector of L components. Okay, that always keep in mind. So you take this derivative, make it to 0. Similarly, you take derivative with respect to W naught, equate it to 0, because that's what happens in optimization. Simply substitute them here, and then whatever you get, slightly counterintuitive it may appear, is that if this is a minimization problem, you would maximize the resulting one. That should not be too strange, because the original one here, when you look at it, is in terms of lambda, you are maximizing it. So for now, you take it to that level. If the primal problem is a minimization problem, dual problem will be a maximization problem, and vice versa. That is all we have to do here. Oh, okay, that's what we will do. Is that steps clear? I know I am just skipping a lot of intermediate things going into any of this math, but this should suffice our purpose, and this is how you will be solved. You can also manage to solve problems without really going deep. It's always good to know it, but I leave that exercise to you. Okay, let's do this. You take derivative of this with respect to W bar and equate it to 0. What is the derivative of differentiation? Derivative I should not perhaps use, because that's single variable. Differentiation of this, very good. I would rather call it W bar. Is everyone convinced why it is W bar? If not convinced, let me quickly write something here. That is nothing but half of W bar transpose into W bar. Right. Now, this is nothing but, let's say, W1, W2, that's enough. Let us take 2 dimensions just to get an intuition, right? If I now also generalize it, there is no point. Okay, W1, W2. That will give me W1 square plus W2 square. Of course, I have half here, I have half here. Now, this means first you take with respect to W1. What is the value of this derivative with respect to W1? 2W1, 2 gets cancelled out, you have W1. Next time you take with W2. What do you get there? 2W2, 2 gets cancelled out, W2. So this should be so obvious to you, because We are always dealing with vectors. The moment you see the derivative of W bar transpose W bar, its derivative is 2W bar. This has to be very obvious to you. Okay. If not, you can hope you all are convinced from what we did with a simple example. Not difficult to generalize. You have n terms. Every time you are taking nth derivative, W subscript n, only that term will remain because these are partial derivatives. And that's how it would come. Is that clear? Right. Good. So then, just for my space constraints, not spatial, I'll just erase that. I would write W bar here. Right. What else next? This one more guy is there. So let me, before I jump there, W bar transpose into X I bar is equal to, can you tell me something? I was telling you earlier, can I use transpose here? Will I get the same result? I can write it if you want, Xi bar transpose into W bar. See, it is just multiplication of the corresponding elements. I could write it this way also. Now, if I am taking the derivative of this with respect to W1, W2, W3, only that X1, X2, X3 components would remain there. So now, derivative of this will be, now what is that value now? Can you tell me? Very good. Xi bar. This is also something, these are, I mentioned you three things. They should be hardwired for you. W bar transpose W. If you are taking derivative with respect to W bar, what you get is 2W bar. W bar, again, we are just talking about vectors here. W bar transpose Xi bar will be equal to Xi bar transpose W bar. If you take with respect to W bar, only Xi bar would remain. Okay, even if you see it, don't get panicked. This is same as this and put same as X bar. Is it clear? Good. Now, so this term is W bar minus, what do I get here? Now tell me, with that background. Minus, you don't want any summation? You got fed up already with summation? I equal to 1 to n. What about this term, by the way? When you take derivative, 0. What about this term? 0, right. All you are left with now is lambda I, yi, xi bar. Lambda I, yi, xi bar. Okay? Yeah.
So each element of the lambda vector corresponds to each training sample.
Correct. The weight you give to, see here, notice here there are n constraints. For each constraint, the weight you are giving to that particular constraint. There are n samples, then there are n inequality constraints that you are posing here. Clear? Good. So let's complete the last one more derivative. And then let's have a peaceful look at what is the outcome of those derivatives by dou W naught. What would be with respect to W naught? What will I get here? 0. Yeah, minus summation. Okay, summation of I equal to 1 to n lambda I yi. So by the way, what should I equate it to? 0 here. Okay, this should be equated to 0. Then I will drop this minus to plus here. These are the two KKT conditions that you obtain as a result or as in the process of solving this optimization problem. Now, what is the next step now? Is to get rid of this W bar and W naught. Can I get rid of them? This W bar, if I substitute, see here, from here, can I not compute W bar? Does it have W naught? No. So if I substitute here, W bar and W naught, I could get rid of that. Lambda I yi is equal to 0. Well, that you can see here what would be the consequence of that when I substitute here. This I is varying from 1 to n. W naught has nothing to do with it. Take this out, right? When I take that out, this term also gets rid of that. And now your problem is just an optimization problem in lambda I. Please do that now. You substitute them there and see many interesting things are going to happen now. If you just stare at the board, they might not happen, but try working out. Maybe instead of putting too many steps, let me also show you something here. When I substitute here, perhaps the convenient way to look at it is W bar transpose times W bar, correct? So what did you get here? Since I have the luxury to erase here, I would write it as W bar equal to this thing. Okay, so I'll just make it. And so this is my W bar is this, and this is lambda I yi equal to 0. So what is going to happen? This term is 0. Okay, I don't want to write too many steps, so I'm just putting it here. This is as a consequence of substituting this result. Okay, and then what? You substitute. So this is nothing but W bar transpose times W bar. What do you get there? I equal to, so you multiply both, you get one of the summations you call as I, another as J. What is it that you are getting there? I equal to varying from 1 to n, J is varying from 1 to n, lambda I, lambda J, yi, yj. One of them is transpose. These are vectors, so their transpose is same. These are scalars, transpose is same. But when it comes here, you get xi bar transpose xj. Of course, you all know it is same as xj bar transpose xi, even if you want to write it. Can you say about this term? What about this term? When I substitute here the lambda W bar, there is I equal to 1 to n is there. Now, so you don't use the same index and mess up the whole stuff. Okay, this you have to be careful. So use again, now use J here for a reason. So J equal to 1 to n. When you substitute it, what is going to happen? Lambda I, yi are there here, xi are there. When you are substituting it, you will get lambda j, yj, xj. There is a transpose here. You are getting one more transpose there. So exactly you will get half minus full term there. Do you see that? I think it is easier to show here. It is less time consuming and perhaps easy to visualize also for you. This is just half of this term. Without this half is what you are getting here. This happened not out of the blues, because your W bar has lambda I, yi and xi. In this term, the lambda I, yi and xi are already there. Then W bar transpose, this transpose is in both places. That is, there is nothing magic happening here. Okay, the very way the W bar is there is multiplication of lambda y, I, xi bar. These are already present here in this term. That's all. Is everyone able to visualize that? So now let me call the resulting problem as L some tilde of, now I am getting it simply in terms of lambda bar, my problem. So what is the result of that? I have 1 minus 1 by 2 into, correct, summation. I is varying from 1 to n, j is varying from 1 to n, then what? Lambda I, lambda j, okay, yi, yj, xi bar transpose xj. Any other term remaining there? Right, very good. I have here summation I varying from 1 to n lambda I. This is a maximizing problem. What you will do, you maximize here. This one, that's what I was telling, right? This is half minus full term. So that is minus half is there. Yes, yes, yes. Yes, sir.
How did we reach from minimum to maximum?
Yeah, that's what you go through the theory. Essentially, you have a minimization problem in terms of W bar and W naught. Lambda term is the dual problem becomes a maximization problem. If it is a minimization, this becomes a maximization problem. Okay, that more than that, I'm not very sure how to intuitively explain that. All I would say at this point is, one way to look at it is the original constraints are maximization. So that way you can for now convince yourself and later go into more detail. Right. This is the problem to be solved. Maybe it is not so obvious yet for you on what exactly did we gain in doing all this jugglery and gymnastics here. Right. So let's have a closer look into this, what you got here as a result. Look at the original problem there. What are your problem? Maybe before that, let me draw your attention to this point. Should I have to assume that I have n number of points, n number of feature vectors? Maybe if you are not convinced with the word points, in your training data, you have n number of feature vectors. Should I have to impose this constraint for all feature vectors? Or if I impose to some, it will obviously be satisfied by the rest? Should I impose this constraint? What is this constraint? Try to have a visualization for that, then you would realize. If you impose these constraints, for which points it is good enough? Very good. If you impose this constraint to support vectors, obviously this is satisfied for all the rest. Why is it so? Support vectors are the closest ones. The moment you are saying that this is for support vectors, what is this value, by the way? That is 1. Okay. So in your optimization problem, you will not in fact do it for n feature vectors. Assume that you have n subscript s support vectors, you have only n subscript s conditions to be imposed, which in other words means that your lambda bar, the rest, you could simply make the corresponding lambdas to be 0. That means you have only n subscript s lambda values to be optimized. Point number 1. Is this clear? You simply make the rest to 0, impose the constraint. See, suppose here I have this support vector, this here, this here, 5 I have. Just for these 5 xi, yi values, you put this constraint, lambda I, make it non-zero. For all the rest, make lambda I to be 0. If you put that constraint here, the rest is already satisfied. So you don't have to do anything in your process of optimization. You just play with only these ns values of lambda. Is this point clear? This is a very, very important thing that you need to understand. Otherwise, you won't be able to. Yeah.
So the number of support vectors for both classes is same, right?
Need not be. Assume here I have 3, for example. See, what are support vectors? Which are lying on these marginal lines. That depends on how it is spread. No. See, the whole thing is my ns here is 5. That's all. I have 3 here, 2 here. So total ns equal to 5. That means I have just 5 points. Is this point clear? Good. The next point I want to draw your attention to. So by the way, before that, look at this original problem. I have, suppose my feature vector is, I'm giving my whole image as an input. So some of you who are doing some deep learning course, you want to do digit recognition. You have a 100 by 100 image. What is the size of your feature vector you typically do there? You give each pixel as a 1 feature. Suppose if you are doing in that crude way, which most of the times we do, unless you have a better thing or better approach. You have, what is the size there? 100, 10,000. Your feature vector size cap L, this W bar is of 10,000 dimensions. On the other hand, not all of them will be here. This size will be very minimal compared to that. So your optimization problem, you are solving it at a very low dimensional space here, because you are worried about only those radicals who are standing near the door, who will, it means you are not worried about, anyway, all the rest are outside. You ensure all your conditions with the guy who is standing at the door. That automatically takes care of anybody outside the door, and it doesn't really matter how many are there. N doesn't matter. Not only that, the dimensionality, you could make some more observations from here. What is it here? This is nothing but a dot product between two vectors. Your W bar transpose W bar, right? I could write it simply a dot product. Dot product between Xi bar and Xj bar, which are of L dimensional space. So that is also something which is helping you, irrespective of their size. It will be just a scalar here. It is not going to impact you. And this you will not, in fact, have to do it for all N. You just do it for those set NS set, because anyway for the rest, this will be 0. Am I clear? You make a subset again, you just change your indexing from 1 to NS here, and then you simply, instead of that, you write here NS, you write here N subscript. Yes, you are done with it. Do you see how drastically it has brought down your dimensionality? Means, of course, here the very assumption is you are not in something like I have drawn on the board x1, x2. If it is there, that's altogether a different story. That's for convenience of illustration, we are doing that. But in practice, particularly when you have feature vector in a very high dimensional space, the moment you take the dual problem, what you need to solve has drastically come down to a lower dimensional space. See, what is it that you have to find out as a result of this optimization problem? Lambdas you have to compute, that is all. And how many lambdas are there? Other than NS lambdas, all the rest are 0. So you do optimization only for NS. Then how do I get, after I get these lambdas, finally what should I get? I should get a line. That means I should have W bar. How do I manage to do that now? Right, that's all. What is my W bar here? Do we have somewhere that? Yes, this is equal to I equal to, now let me write it as 1 to NS lambda I yi xi bar. Did you notice here? So again, keep in mind that my indexing is re-indexed now, okay? Because earlier this might be somewhere else. It's not like x1, x2, x3, x1, y1, x2, y2. If I have, they will not simply become my support vectors now. I'm just collecting all my support vectors and giving some new index to them. That's all. So this is how I am going to have W bar. Again, this is not the only consequence of it. You will see, perhaps I may discuss in the next class, nonlinear. This is linearly separable, right? Suppose if you have nonlinear classifier also, then you would see this dot product has a very interesting consequence, which we would see. So just still keep yourself open that there are other incentives also that you are going to get out of this, which we would analyze once we discuss something else. Then that becomes very clear to you. Okay. NS will also change for lambda I summation NS here. Yeah, yes. This is also NS. Yeah, otherwise also doesn't matter. The rest are zeros, so doesn't matter. Okay, is that clear?
But sir, you mentioned that we are reducing the dimension. Doesn't that mean that we are reducing the number of features that are described?
No, nowhere. That is the beauty of this. See, is there anywhere we are, see, what is our final goal? I want to get a line. How do I get it? I either calculate it from x1, y1, x2, y2, x3, y3 in the way, how do you do that? Your g of, let me write it this way. Your g of x bar equal to w bar transpose x bar plus w naught, right? You do with all x, y you do that. But is it what you realized out of this SVM is you don't really have to worry about the rest. You just see the borderline cases and just they are the ones which would decide how this would behave, right? That is what you achieved here. Can you rephrase your question and again?
No, when you said dimensionality reduction.
Dimension, it is not, don't confuse this with the dimensionality reduction. All I am saying is you are optimizing a problem where the dimensionality of the parameters to be optimized has come down. This is nothing to do with the dimensionality reduction, which other methods like principal component analysis does. That and SVM are different. So this is not that dimensionality reduction. All I am saying is number of parameters to be optimized have drastically come down. Is that subtle difference clear? Subtle but important. Say suppose here also what I could now do is, since anyway I have written it, let me write that I equal to 1 to ns lambda I yi x I bar, maybe I should write there transpose, correct, into x bar, or let me call this as new point xp. So xp bar, will it not go inside? Should, plus w naught. What? See, if you are given a new point, okay, you are done all this thing, you got this w bar this way, and a new point has come, new feature vector has come in the testing. You want to see where it goes. One way is anyway you know w bar, right? You calculate it over all the points. Another way is this also is good enough, because your w bar, if you look at it there, that is lambda I yi xi bar, and your lambda is non-zero only for ns. So that you could use here, and you could right away calculate from this. One more point here. This is a convex optimization problem. Why is it a convex optimization? W square is there. That say x square is a convex thing. So what is ensured here for sure is it is independent of your initialization of W bar. You will arrive at the same hyperplane, whichever is your initialization. But don't confuse that with these weights. These are not unique. It is just like you have different waveforms. A particular waveform can be generated by giving different, there could be different ways you could combine this to get the same final result. If you look, compare it with, I have a particular waveform I want to get. It is so, means when all the basis functions you have are not orthogonal, you could have different combinations with which by combining the basis vectors, you could arrive at the same result. So here, when we say the solution is unique, don't compare your answers with your friend's answer in terms of lambdas. Okay, you compare it in terms of your hyperplane. Okay, that you please do. Don't do it and don't match everybody's results there. Is my statement clear? W bar is unique. No. Yes. See, you could have, see, you could, depending on your initialization, you could get different lambda I vector would be different. But if you compute the hyperplane, which is represented by W bar, that is what characterizes that hyperplane will be same. So when we say there is a unique solution here, mistake not that the unique solution is not in terms of the lambdas you are getting here as a result of your optimization, but the uniqueness is in terms of the hyperplane that you are getting. You all should be getting the same hyperplane. It's like all people have got summation of marks might be 300 out of 500, where 5 subjects are there, but the way they got in each subject were different, but finally ending up with 300, something like that. No. That's what I'm saying. It is the final hyperplane that will be same. Not necessary. Not necessary. See, if I say that finally everybody got 300, I could come up with out of 5 subjects, I could always have different weights to them and arrive at 300 marks there. This is very similar. This is not too far from the scenario that is there. This lambda I is weighting yi and xi bar. I could have different weightages, but still final result could be 300. 300 is like a hyperplane. These weights I give are the lambdas. Clear?
And this is classification of a new point.
Exactly. To classify a new point, one thing is hyperplane I am telling. Hyperplane will be unique, so mistake not that. You will get different hyperplanes. But the lambdas that you are getting as a result of minimizing this or maximizing this dual problem could be different. Right. Exactly. So as far as the hyperplane is concerned, it is unique, which was not the case with either with the neural networks. The other one you could get correct. So if you change your initialization, neural network could give you different hyperplanes for each initialization. Just like I have some points here, okay, some points here, I could draw different set of classifiers here. So your neural network can give any of these things depending on where you initialized, but your SVM will always give you where this got maximum, irrespective of the initialization. So only point on top of it I am telling is, don't mistake not that uniqueness with the values of lambda. Compare your lambdas from different implementations or what you got from different initializations, because here also you have to initialize somewhere for the algorithm to run. But then depending on the initializations, lambdas would change, but this hyperplane would remain same. Clear? See, as this is a convex optimization problem, wherever you start, you arrive here. This is a linear combination of these vectors. You could always find out a different weighting given, arriving at the same result. That is all we are saying. Okay, good. Maybe in the interest of time, I have to stop here. Next class, I will give you an outline of the SVM for what is this. What we have seen is linear separable. So easier one next to continue is linear non-separable, that we will do, and the final optimization part perhaps I'll leave that to you, and then maybe after that I'll also go through another important one, nonlinear separable. At least I will give you some outline, because that is something you would encounter in practice more than linear separability. But anyway, this is all the basis. It's just a small hop you do on top of it. Okay, yeah, we'll stop here.